We're talking about shapes of molecules. So if you approach a problem about shapes of molecules, start off with drawing the Lewis structure. Even if it doesn't say you have to do the Lewis structure, you almost always have to draw the Lewis structure, or at least if you have a lot of practice, you can visualize it. Next thing there, we're going to do something called the steric number, and different people call this different things. We might call it charge clouds or call it electron regions. We will define our steric number. And then there are 5 basic shapes, based on the different steric numbers, and you have to know those shapes, and then you have to kind of visualize, well, what would we call the molecule if it had lone pairs? So if you are just talking about the 5 basic shapes, we're talking about the electron geometry, and when you take into account the fact that some of the electrons do not have atoms on the end, they're just lone pairs, then we'd be talking about the molecular geometry. Typical question might be one here from the National Chemistry Olympiad, and it says, what is the shape of the ClF3 molecule? And we have 4 choices. So we'll come back and visit this question in a minute. So steric number is the number of bonded atoms and the number of lone pairs. So we'll do a couple examples for this carbon atom, and usually we only do the central atom because that defines the shape. But so this carbon has 1, 2, 3, 4 bonded atoms, and there are no lone pairs on that carbon, so it has a steric number of 4. Now other people might say it has 4 electron regions, or however, I call it steric numbers. For this carbon, we say it has 2 bonded atoms. The fact they're double bonds makes no difference. So 2 bonded atoms, and there are no lone pairs on the carbon, so this one has a steric number of 2. For this carbon over here, we have to decide, well, what do we want to talk about? Well, we could talk about either one of these. The carbon has 1, 2, 3 bonded atoms, the hydrogen, and the carbon, and there are no lone pairs on the carbon, so this has a steric number of 3. Now we go back and learn that if there's a steric number of 2, then we're talking about a linear molecule, because 2 regions of electrons would repel each other at 180 degrees. If we had the steric number of 3, then that is going to be trigonoplanar, 3 things at 120 degrees. 4 would be tetrahedral, 109.5 degrees. 5 would be trigonobipyramidal, and we would have 2 different bond angles. We'd have the 90-degree bond angle here, and around the middle, around the equatorial position, would be 120 degrees. And a steric number of 6 would be octahedral. Top, bottom, left, right, like that. So if we start with, say, the octahedral, a steric number of 6, well, we'd see a particle and we say, SF6, somebody wants to do SF6. Well, sulfur is going to take 1 electron to hook on each of the fluorines, and I'm just going to put them around like this, and then I should go back and put all my lone pairs on. This is pretty messy. But the idea here is that sulfur has, 6 valence electrons, and it has used all 6 valence electrons. And so I have a particle that has a steric number of 6. There are no lone pairs on the sulfur, and so my molecule is going to be, the electrons are going to be octahedral, and also there's an atom on the end of each pair of electrons, so it's also octahedral. So this molecule will be octahedral. When we get to ClF5, I'm going to try this a little bit better. Then chlorine has 7 valence electrons. I need 5 of them to hook on my fluorines. And that leaves me with 2 electrons, which are going to be together as a pair. And I need to put on my lone pairs. So this has 5 bonded atoms. It has 1 lone pair, so again that's steric number of 6, but this time because there's a lone pair, then we don't count that for the shape. It's there, it keeps everything being kind of octahedral, but what's left over we call that square pyramidal. If we were going to do XE, then we could say, XE has 8 valence electrons. So we'd say xenon. Now it's going to take 4 of them just to hook on the fluorines. That leaves us 4 more, which will be in pairs. So again, that's going to be a steric number of 6 with 2 lone pairs. The lone pairs are going to be opposite to each other because they repel more than bonding pairs. So what's left over is square planar. So this would be square planar. Now you can see that if we had one with 3 lone pairs, what would be left over would be T-shaped. If we had 4 lone pairs, what would be left over would be linear. And if it was 5 lone pairs, it would be linear. And I don't know of any examples of these other molecules. There's too many electrons. But just to complete the pattern, we could see that. So I think you're really only going to see examples of these top 3. So steric number of 6 could be octahedral. Okay, it could be square pyramidal, could be square planar. Now we'll go to steric number of 5. Okay, steric number of 5, here is PCl5. So if we were to draw the phosphorus, okay, it's going to take 5 valence electrons just to hook on the chlorines. And it turns out phosphorus has 5 valence electrons. So that's pretty much our picture. We'd have to put lone pairs. So steric number 5, no lone pairs. 5 has a shape of trigonal bipyramidal. 1 up, 1 down, 3 around the middle. And we would see that on the other page. It looks something like this. And what would happen is this, there is an atom at the end of each one of these, then the shape of the molecule is trigonal bipyramidal. When we get to sulfur, SF4, okay, it's going to take 1 electron to hook on each of the fluorines. And that leaves 2 more because sulfur has 6 valence electrons. So steric number 5, but this time there's 1 lone pair. Now be careful here because this is the one time where putting your lone pair does make a difference. It goes in the equatorial position, the 3 that are at 120. And the reason is that lone pairs repel more than bonding pairs, so you want to put them in the more spacious position. So what do we have left? We call that seesaw. Old-fashioned, I've seen distorted tetrahedron, and I've seen another name, but most people call it seesaw. And it, if you kind of think of it sideways, sort of looks like a little seesaw. Now ClF3, okay, ClF3 be Cl in the middle. Okay, we'd need 3 of our 7 electrons to hook on our fluorines, and that leaves 2 pairs. So we have steric number of 5 with 2 lone pairs. So again, both of those lone pairs are going to be in the equatorial position, so we're left with a T-shaped molecule. XeF2, okay, xenon has 8 valence electrons. We can use 2 of them to hook on the fluorines, and that leaves 6, which would be 3 pairs. Steric number 5, 3 lone pairs. All 3 are in the axial position, so what's left over is going to be linear. I don't know of an example of this one. Okay, if we have steric number 4, okay, we can see that CH4 is going to take 1 valence electron to hook on each of the hydrogens. Steric number 4, tetrahedral, no lone pairs, pretty easy. When we get to ammonia, okay, nitrogen, it takes 1 lone pair to hook on each of the hydrogens, and nitrogen has 5 valence electrons. I think I said that wrong. Nitrogen is going to take 1 valence electron to hook each of the nitrogens, and we have 2 left over. So we have a structure like this. 3 bonded atoms, 1 lone pair, steric number of 4. But because that lone pair, okay, there's no atom on the end, what's left over looks like a little triangular pyramid, so we call that trigonal pyramidal. Okay, water, classic structure. Okay, oxygen, it's going to take 1 of its valence electrons to hook on each hydrogen. That leaves 4 more, 2 pairs, steric number of 4, 2 lone pairs. Okay, we get a classic bent shape here for water. And let's say hydrogen fluoride. Okay, we could do this again. So fluorine, okay, takes 1 electron to hook on the hydrogen. That leaves 6 left over. And we could say that this was a linear molecule. Anytime there are 2 atoms stuck together, it's always going to be linear. So there's no way that 2 atoms can't be linear. If we're talking about boron trihydride, okay, it could be in the gaseous state, this is a covalent compound. And so what happens, we have 3 valence electrons on the boron are used to hook on the 3 hydrogens, no lone pairs, steric number of 3, so the molecule and the electrons are all trigonal planar. Sulphur dioxide, okay, sulfur, okay, has 6 valence electrons. So if we draw this, we're going to make a double bond to an oxygen, we're going to make a single bond to an oxygen, and that leaves a lone pair on the sulfur. Now this would have a resonance structure where we have sulfur with a single bonded oxygen and a double bonded oxygen and a lone pair on the sulfur. Anyway, if we look at the sulfur, we say we have 2 bonded atoms, we have 1 lone pair, so that's going to be a steric number of 3, and a steric number 3 with 1 lone pair. Okay, there's no atom on the end of that, so what's left over would be bent, or some people say angular, some people say V-shaped. And again, anything that had 2 atoms would be linear as well. Okay, then if we just have 2 atoms here, it's just going to be linear. That needs no explanation. So if we kind of put it all together, okay, we have to try to learn, the steric numbers. So look at a molecule and say, is it 6 or 5 or 4, 3, 2, and 1? And the shape of those are octahedral, trigonal bipyramidal, okay, tetrahedral, trigonal planar, linear, and linear. And that would be the shape of the electron pairs, if somebody asks, or you say the electron geometry. But if there are lone pairs, so that there's no atom on one of these corners, then we have to learn what the shapes are. And I would, not really memorize. I would just go through this and make this make sense for myself. So I had to go through and say, okay, octahedral. If there's 1, it's square pyramidal. If there's 2 lone pairs, it's square planar, T-shaped. Same thing for 5, trigonal bipyramidal. Okay, remember this is got to be careful because the lone pair is in the equatorial position. So seesaw, T-shaped, linear. And 4 would be tetrahedral, trigonal pyramidal, bent. And then trigonal planar, okay, bent. And these are all linear. So let's go back and look at our question. So what is the shape of the ClF3 molecule? First thing we have to do is to draw what the ClF3 molecule will be looking like. Okay, chlorine has 7 valence electrons. It's going to take 3 of them to hook on the fluorines. Now since I had 7, I just used 3. I have 4 left over, so it's going to be 2 pairs. So I have a steric number of 5. So steric number 5 is basically trigonal bipyramidal. But I have 2 lone pairs, so one of these will be a lone pair, one of those will be a lone pair. So what do I have left over? I have this, this, and this. Okay, so my molecule is going to be T-shaped. Answer C. And that's what goes on with shapes.